Mr. B. Dhanasegar is working as a lecturer in Department of Information Technology, Anna University, Chennai. He finished his MCA from Urumu Dhanalakshmi College, Bharatidasan University. He finished his ME in Computer Science and Engineering from College of Engineering, Anna University. His areas of interest are multi-core programming and architecture, programming models, compiler, automata theory, cryptography, and algorithms. He is an expertise in subjects like compiler design, formal languages and automata theory, analysis of algorithms. His research area is code generation for multi-core architecture.
Welcome to the UGC lecture series on computer science. We have theory of computation as far as this series of lectures is concerned. So, I will start with the what we had as far as the previous episode of this particular lecture series is concerned. So, we are studying the representation for Turing machine. It can be either the transition table representation or it can be the transition diagram representation, just like what we have done for the finite automata and the push down automata. So, the only difference among the transition diagrams from that is the finite automata represent for transition diagram for finite automata, or it is going to be PDA or it is Turing machine, is on the labels, like that is what will be there on the label which is connecting the pair of that is states. So, in the case of finite automata it is going to be a single symbol, and whereas in the case of push down automata we will be having both the input and output, that is reflecting that is what goes on to the that is a stack also. But whereas in the case of the Turing machine it is the tape content, actually what we read from the tape and what we will do on the tape. That is like when you are reading x, and if there is a need for replacing it by y, we need to represent both, that is x and y, on the edge connecting a pair of states. Also, that is after replacing the current symbol, that is after processing the current tape symbol, then what is the direction in which we need to move as far as the tape is concerned. So, it is going to be 3 number of symbols which are there on the that is edge connecting pair of states in the Turing machine, the transition diagram meant for Turing machine. Then as usual we will be having the starting state which will be marked with a small incoming, that is edge arrow which will be labeled normally with start, and the final state is marked with the double circles, saying that that is going to be the place where the Turing machine halts with acceptance. So, at any stage if you find that there is no valid move from the current configuration or from the current state, then your Turing machine is going to halt without accepting the string. So, in that case we will say the Turing machine halts without acceptance. So, as far as this episode is concerned, we will be having something like there is when do you call a Turing machine is getting halted. So, at any stage if you find that the Turing machine there is not finding a valid move from the current configuration, it may be because of actually all the transitions which are valid or which are needed for the current, that is Turing machine, or the Turing machine for which we have the problem for which the Turing machine has been designed. So, if we have a move, then we will do it, and moreover we will write only the moves which are required for the construction or required for solving the problem which is given under which is given for us. We will not write the invalid moves. So, if the invalid moves are there, then we can take care of those moves and appropriate error messages can be displayed. But in the simplest cases like the simple Turing machine design, we will not account the invalid moves, we will keep them as blank. So, when there is a need for looking at the blank entries, so your Turing machine cannot move further. So, we are looking into a blank entry only because of the Turing machine or the input available on the tape is not going to be valid one, or it is not in the language of the Turing machine, or if it is not going to be a valid computation, then we will say that the Turing machine will not be able to find a valid move from the current configuration. So, that is a place where we will say that your Turing machine is strictly going to halt, because it cannot find out any valid move. So, we will say it is going to halt, but the halt is not denoting the acceptance of the Turing machine, but it is going to be a rejection. So, that is what we call it as it is going to be a reject. If the Turing machine is going to halt with it is not there, if the halt is happening in a state which is not going to be a final state, then we will be calling it as reject. And if the current state is going to be in F, that is F is going to be set of all final states. If it is in F, then the Turing machine is going to halt, because as far as the Turing machine final states are concerned, there won't be any valid move from the final state. So, once we are in the final state, and if the Turing machine is going to halt now we can say that the Turing machine is halting with accept. So, two cases, either the input would have been accepted or it would have been rejected. So, it is all depending on which state we are. So, whether the state we are in is in F or it is not in F, then we can say that whether the language is going to be accepted or rejected. As far as accept is concerned, it should happen only on final state, but as far as the reject is concerned, it may happen at any stage, but not the final state. So, that is what we are saying, that the Turing machine may halt at any state. If the halt happens at final state, then the input is accepted. So, when it halts is going to be either we are in final state, it may halt, or we will be halting when we find that there is no more transition from the current configuration. That is, if there is no transition defined from the current instantaneous description, then we will say that it is going to halt. There is another category of that is Turing machine where we may not halt, like we will be doing some job and we will find that always there is a valid move available, and we will never reach the final state, or we will never find a configuration where there is no valid move there. In that case, your Turing machine keep on that is doing some job either wanted or unwantedly, and then the Turing machine will never come to a halt. So, it is going to be a situation like the Turing machine is not halting. So, based on this only we will be defining two classes of that is languages. One is called the recursively enumerable language and another one is called the recursive language. So, generally the Turing machine language is considered as recursively enumerable language. So, if the that is the Turing machine accepts some language, then definitely we will be that is calling the language as recursively enumerable language. The normal definition, like we will be having a starting configuration, and then there is a that is the input available on your tape, and then something is happening, some recognition is happening. So, the language of the Turing machine as far as Chomsky hierarchy is concerned, it is going to be recursively enumerable. But there is another class of language we have called that is recursive. So, what is the difference in between these two, that is class of language like recursive and recursively enumerable? So, if the Turing machine is guaranteed to always halt, then it is required that the Turing machine has to halt, but there is no constraint about whether it is halting by accepting the input or halting by rejecting the input. So, either way it can be, the Turing machine is expected to halt, but it can be either an accept and halt or it can be a reject and halt. If it is always guaranteed to happen that your Turing machine halts, then the language we call it as that is recursive language. So, this will be directly related with algorithms and that is from that related programs, like algorithm is expected to always halt, but whereas it is not required that a program should always halt. So, if you are having the Turing machine whose language is recursive, then there is always an end available or always a halt available. So, it is equivalent to say that an algorithm exists, then the language is called recursive. But if the Turing machine which we have designed is not necessarily to halt always, for some input maybe it will be halting, and maybe if it is a valid input it may be expected to halt, but if it is going to be an invalid input, instead of halting, if it is doing some job here and there, then the language is called recursively enumerable. So, there is no guarantee that your Turing machine halt even after some amount of time or any amount of time. So, that can be that is mapped, these kind of problems cannot be mapped with algorithms, because the very important property of any algorithm is the finiteness. After some finite amount of time, after consuming finite amount of time and making use of finite amount of resources, then the algorithm is expected to halt. But in the case of recursively enumerable languages, the algorithm not necessarily, that is the Turing machine is not expected to halt always. That is why we have two classes of languages, one is the recursively enumerable and another one is going to be the recursive. So, here we have the definition, that is, if Turing machine is always halting either by accept or reject. It is not strictly required that you should always accept. So, either by accepting or by rejecting, then the language is called recursive, and the language of the Turing machine is called recursively enumerable. In that case, there is a chance even for not halting also. Here there is another way of representing the recursive language is, so LM is going to be the language of the Turing machine M. If it is to be called as recursive, but the condition is any x belonging to LM, the M has to accept x, and if some string that is y, if it is not there in the language M, then M should reject. So, always we will accept provided the input is valid one, and if the input is not a valid one, then we will not accept. So, if the input is valid, it will say that it is going to be accept and halt, and if the input is not valid, it will say that the question is going to, or the problem is going to be a reject and halt. So, in these two cases, these two combination will give you, there is going to be the language is going to be a recursive language. Next one is like we have some provision for that is including more facilities on the Turing machine. The standard version of the Turing machine is going to have a single tape and a finite control. The finite control is just holding what is going to be the current state, and based on the current state, the current tape symbol available on the tape, we will decide on what should be the next course of action. But now we have a concept called storage on the finite control. The storage on the finite control means that is, instead of just holding what is going to be the current state of the Turing machine, we can extend the current, that is finite control, as a tuple with some number of locations, maybe k or l number of locations, and each location is capable of holding one symbol at a time. So, what is the advantage in it? It is possible to remember there is one or more number of symbols which we have most recently recognized. In the earlier cases, it is still possible to give some interpretation for what is the input, but we need to use more and more number of states for differentiating what is going to be the first input or the first symbol or the second symbol or anything. Maybe if the first symbol is 0, we will be jumping to a state maybe q1, and if the first input is going to be a 1, then we can go to some other state called q2 or q3. So, based on whether you are in q1 or in q2 or in q3, we can differentiate whether the input the first symbol is going to be 0 or 1 or 2. But if there is a chance for recording what is going to be the first symbol, then we can be in a unique state, and still it is possible to know what is going to be the first symbol which is there in the Turing machine tape. So, where do you store that? So, that is going to be the question. If you want to store it, we must have some location, and now we are including those locations along with the finite control. So, we call it a storage, and now the finite control is considered as a tuple with the state as usual, that is mandatory, which is denoting what is going to be the state of the Turing machine, and along with that, based on the requirement, we can have any number of locations. So, more the locations we are having, and more the problem will be complicated. So, based on the need only, we will be defining the number of storage locations required. 1 or 2 number of locations we can fix, so that we can have some input on, we can record some input on the Turing machine, that is storage control, that is your finite control and its storage. So, whenever we need to map these kind of symbols, or whenever we need to match these symbols with some other symbol, and then we can make use of the symbol available on the storage, so that it is possible to compare and do some operation. So, that is the advantage in going for the finite control. So, here we have the description about the storage in the, that is the state. So, each finite control, that is the finite control of the Turing machine, for a single, that is Turing machine, there is only one finite control available. Here we have a finite control, and the finite control holds finite amount of data along the that is state, and how it will be represented now. So, earlier we have only, that is q, that is a finite control the state. So, now we have different locations L1, L2, L3 etc. up to Lk, where k number of locations on the storage tape of the symbols. So, what is the need for that? It is actually allowing us to describe the transitions in a systematic way. We can record symbols, and we can make use of the symbols wherever it is needed. That is what the help of that is the purpose behind the introduction of the locations L1 to Lk on that. After a short break, we will continue this lecture. Welcome back after the break. Now see that is how the transitions are all carried out provided if the storages are introduced. In the absence of storage, we have only a state called Qi and then the input, which is input, I mean that is a tape content, the current symbol, and based on that we will decide what is going to be the course of action. So, if A is there, then if X is the output, it means that the replacement given for A is going to be X, and after that the direction to be moved is going to be R. But now after introducing a finite control, there is storage on the finite control. Here actually I have introduced only one storage on the finite control. Before copying anything onto the storage, we find that only a blank is there. So, we say that blank is available, we write inside the square bracket only one storage location, and the current input symbol is A, and what is going to be the output. So, Qj comma A is the output. It means that we have recorded the most recently scanned tape symbol onto the finite control. So, Qj comma A, and one more action what we have done is replacing this A by X. So, it is going to be here is the description. It records the current input symbol A in the storage and replace A by X in the tape. If you look at the next one, you have that is del of Qi comma A is equal to Qj comma blank comma A and R. So, it is actually clearing the buffer content. So, either you can record symbol on the the storage which is in the finite control, or we can even clear the finite storage on the finite control. So, it is going to be A actually available, the output is from Qi you jump to state called Qj, but the input which you have stored on the tape is no more since we have made it as blank, and the output the tape content is not at all disturbed, and we still move with the right direction. So, that is not a important thing. So, the how we are clearing the buffer content is very important. Here we have recorded the input onto the buffer, that is storage, and here we are clearing the buffer content or the storage by using the blank symbol. So, both can be done as far as the storage on the that is your Turing machine finite controls are concerned. So, we can construct different kind of Turing machines with the help of the storage. So, wherever there is a need for finding matching symbols, especially with finding the palindromes, or even that is ensure. Here we have one simple example, we start with 1 and thereafter there is no 0, no 1, or suppose if we start with 0 then thereafter there is no 0. So, that is the meaning of this pattern. If I start with 1 then I can have only zeros, if I start with 0 then I can have only 1s. So, in this case we must ensure that if the input starts with 1, then there is no question of having a 1 anywhere in the input, remaining part of the input. Otherwise, if the input start with a 0 and then nowhere else, there is no question of having 0. If you are very sure that only one pattern is available, even in the absence of storage, it is possible to do this. You can make use of a state that records 1 and there is no more, there is 1. But since we are having both cases, the input may start with the 1 or it can even start with the 0, and what we want to ensure is the first symbol should not be repeated in both cases. So, if you have a storage or if you are having a provision for recording the first symbol, then we can very easily map it with the rest of the symbols, ensuring that it is not matching with the remaining symbols on the tape. So, look at the way in which we are writing the transitions, we are having the initial configuration. We start with Q0 and B, it stands for the blank. Initially we have nothing on the storage, and we read a symbol called A from the tape. So, this A here it is going to be a variable, you can make use of it as a variable as far as this context is concerned. It can be either a 0 or 1. So, whatever is there, so it is already there in this. So, now you just record on to B. So, there is a location where this the location which is actually there in the finite control, which is meant for recording the symbol from the tape. And now we are moving on to the new state called that is Q1. The reason why we are making change on the state is only Q0 has to record the information, but there is no need of recording by the remaining part of your Turing machine transitions. So, that is the other states need not do the recording of the input. So, Q0 it records this A onto the storage. So, giving you A on that is the storage and leaving A on the input, and now it is going to be a right move. So, we are moving towards the right direction. So, what will happen in the next case? So, from Q1 you are already having A on the buffer or in the storage of the finite control, and now we find that B. So, strictly it is required that A and B are not same, because if A and B are going to be same, then it is once again violating the property of this particular pattern. So, since that is the reason why we have introduced two different symbols there. So, A, but here it is going to be B. So, as long as the current tape symbol is not matching with whatever we have recorded on the storage, there is a valid move that will keep the input as it is and the storage as it is. So, that is what we are doing. So, Q1 no changes for state is concerned. A is going to be the one which you already record on the storage, finite control storage, and B is the one which you are read from the tape, which is not at all disturbed and keep moving towards right. Okay. So, what will happen, that is how do you recognize that? So, we are moving towards right and there is no question of having any more A, but there is a point at which we will be finding only a blank. So, when you find a blank from Q1, then we can immediately say that the input is of the form A followed by only B's, or it is going to be 1 followed by only zeros, or 0 followed by only ones. So, here we have del of Q1 comma A comma B. It means that we have reached the rightmost end of the tape. So, you just leave the blank as it is, no problem, and moreover even we can accept it, that is with the by entering into the final state of the Turing machine, or we can say that even there is clearing the buffer and then accept. So, clearing the buffer is not mandatory, but if you want to, that is clear, we can replace that content or whatever is there in the storage of your finite control, that can be replaced by the corresponding blank. So, this is a problem where we really find the size of the problem or the number of transitions required for doing this problem will be less, only because of we have introduced a storage on the finite control. And we have one more problem here, that is for validating the strings of the form, that is W followed by W reverse. So, these strings are like the palindrome kind of strings. So, if something like reading from left to right and right to left are giving you, that is always the same string. So, the strings can even be, that is the even length or even the odd length strings. So, like 1 0 and then followed by a 0 1. So, this is a case where it is going to be an even length string, or that is 0 1 0, it is going to be an odd length string, but still reading from left to right and right to left looks, that is reads same. So, these kind of strings how do you validate? So, in the case of the recording, that is provides the recording on the storage control, it is so simple. You find out the very first symbol, you just record onto the that is the finite control storage, then keep moving towards the rightmost end of the tape, and we will reach the end of the tape. The end of the tape will be, that is marked with, actually the end of the tape means the end of the input. So, the end of the input, once it is known, that is we will be in the blank, or we the next symbol, or the end of the input is marked by a presence of a blank on the next position. So, once you reach the blank, then you make a move towards left, and now we have the very last symbol available on the input. So, this input must be same as, or this tape symbol must be same as the one which we have recorded in the final storage. We record the storage, that is we record the symbol from the storage from the input onto the storage, then we will move, reach the final state, identify the final, that is symbol from the tape, and if it is same as the one which we have recorded on that, it is the first symbol has been matched, the first from the left end and the right end both are mapped. So, now there is a need for continuing this as long as matching is continued. So, at some stage we will find that the last symbol has been matched and its corresponding symbol has been identified. So, in the case of even length string, and in the case of odd length string, one symbol has been recorded and we are looking for the counterpart, but it is not there. We will come back, and if you are coming to the same position, that is also going to be true, because string with one length is always going to be palindrome, or of the form W is equal to W reverse. And let us see the various transitions required for the doing this problem, that is W is equal to W reverse. So, for validating the strings of the form, that is W is equal to W reverse, where W is from 0 comma 1 star, that is closure, any string from the binary alphabet 0 comma 1. So, we start with the Q0 with nothing on the storage, and A is the current symbol, you record it and make it as blank. because every time the leftmost symbol once recorded it is made as blank, and the rightmost symbol once matched you make it as blank. So, here it is going to be q1 comma a recorded, make it as blank and move towards right. So, now we are moving to q1, and the next symbol, that is second symbol, it can be anything, but there is no need of mapping with a, only the last symbol is to be mapped with a, the rest of the symbols can be simply skipped irrespective of whether it is going to be 0 or 1 or anything, is completely skip. So, q1 will keep on skipping all the symbols until it finds a blank. So, q1 comma a, which is the finite control, b is the current tape symbol, you leave it as it is. So, q1 comma a, leave it as blank and move towards right. The next one, q1 comma a, still on the finite control is in the same thing, same state, but instead of expecting a instead of getting a symbol from the tape, we find a blank. So, what we should do is, now there is a need for a move towards left to find out the last symbol. So, we are going into a new state, that is going to be a q2, and now we are moving towards that is going to be the left. So, we are taking a move towards left. So, making a move towards left will give you the last symbol available on the tape. The last symbol is strictly to be the symbol same as the one which you have recorded. So, from q2, if you have made a left move, we will be having the last symbol, and the last symbol must be a. So, that is what we are having a and a here. So, del of q2 comma a and comma a, that is the current buffer symbol or the storage is having a, and the tape symbol is also, the last symbol available on the tape is also going to be a. So, in that case we can clear the buffer, because the symbol and its corresponding counterpart, the pair is also been identified. So, there is no point in once again remembering that symbol on the buffer, you just leave it. So, it is going to be a blank, and the last symbol should also be made as blank, because that should not be once again compared with some other symbol. So, for that we will change the state q3, and the recorded symbol, that is from the storage, has been replaced by blank, and that is removed. So, the buffer has been cleared, and the last symbol is also made as blank. So, now there is no need of moving towards right, keep moving towards left. So, your q3, what it does is, irrespective of whatever is available on the tape, it will be keep on, that is making it as blank without bothering about, without it is leaving it as it is without disturbing the buffer. So, q3 for any symbol, do not record it, leave it as it is, move towards left. So, q3 for any symbol, no need of recording it and move towards left. So, what will happen, suppose if it is going to be like there is the leftmost blank, the end has been reached. So, that means q3, instead of getting a symbol, we find a blank, it means we have reached the leftmost end. So, once you have reached the leftmost end, once again get back to the starting state, that is q0, and from q0 it is going to be a cycle. So, it is going to be a loop, that is every time it finds a symbol from the leftmost end, and it will find out, it records it, it is going to the rightmost end, find out the rightmost symbol, and if it is matching with whatever is there on the storage, it will, that is replace that last symbol by blank and clear the buffer, come back and enter into the start state called q0. So, now the question is, how do you accept? So, there are two, that is accepting configurations. One is going to be the one with the even length strings, where w is equal to w reverse. So, in that case, from q0, instead of finding a symbol, if you find a blank, you just enter into the final state. So, the string can even be an empty string also. So, in that case the blank, or the string is of even length, maybe it is 0 1, then 1 0. So, 0 0 mapped and 1 and 1 mapped. Now, we are looking for a symbol, but we find that only blank is there. So, you just enter into the state called q4, saying that the input has been recognized. And suppose if it is going to be an odd length string, then where the question will arise is, there is, we have recorded a symbol and now we are looking for its corresponding symbol on the right, but we see a blank. Actually, we are like expecting a symbol from the right, but we see a blank. We will come back. Now, we are in, that is q2, since we are expecting a symbol, but it is not there. So, what we can say that is, this is going to be a single symbol whose pair is not at all there. So, it is going to be the only symbol whose pair is correspondingly not at all there. If the pair is available, then we must ensure that it is going to be the same symbol, and if the pair is not there, then we can immediately declare that it is also going to be a palindrome. So, we can go for entering into the final state, clearing the buffer and leaving the blank as blank, and you can either move a left or move towards that is right. That is about how we are recognizing strings of the form W, W reverse, whether it is going to be an even length string or it is going to be an odd length string with the help of the storage. To summarize, as far as this topic is this episode is concerned, we have seen the Turing machine and its halting property, that is when it halts and when it is not halting. And also we have seen one simple facility which is being provided by the storage on the finite control. And another important point here we have to remember is, just because of introducing the storage control onto the storage onto the finite control, we can't expect that the power of the Turing machines are that is increasing. So, the language is going to be recursively enumerable only, irrespective of whether we are having storage on the finite control or there is no storage or n number of location on the storage. We can't claim that the power of the Turing machine is there is more. It is also going to be same, and we have seen some more examples like the how we are constructing the Turing machines for that. And here we have few problems like W, C, W reverse, where W belongs to some alphabet like 0, 1, and C is going to be a single symbol which is actually denoting the separator for W and W reverse. So, it is much easier to recognize these kind of strings. So, because it is going to be the first symbol and then you go for the last symbol, we know that C is always going to be the middle position, and the next is going to be the W, that is W, where it is going to be an ambiguous case like here. And so, here also if you find that W is C W, then it is much easier to recognize these kind of strings. And then 0 power n followed by 1 power 2 n, that is the number of ones is double the number of zeros available in the that is tape, but in the order, that is 0 power all zeros followed by double the number of zeros, that is ones, that is equal to the double number of zeros, that is in the same order. So, these kind of questions may be that is asked as far as the construction of Turing machine is concerned. So, even simple problems like the problem can be a recognition type or it can be the computational type also. So, whatever it is, you just find out the various transitions, identify that the Turing machine should halt provided the language is going to be a recursive one, and if the input is going to be a valid. If the input is not valid, then it is going to be a halt, but there is no question of reaching the final state of the Turing machine. So, with this I conclude this episode of this theory of computation lecture.